if it was so close together that the gravitational force was bigger than the centrifugal force, but because it's so big, the centrifugal force is bigger than the gravitational force. Or well, it's not bigger because it's still bound, but it's significant.
So why
They
aren't there
can't even say a force is bigger than the weakest force. I'm sorry for interrupting. That's how sacred this cow is. Please continue.
So, Taylor, I think you're asking why a galaxy does not have two orthogonal disks. Is that the question?
Yeah, why is there only just one all the
Because
time?
the galaxy or the protogalactic nebulae had a coherent direction, meaning that it only had one axis of rotation. Therefore, angular momentum is only going to work perpendicular to that one axis. You can only form one disk. If you wanted to form multiple disks, you would have to explain why the angular or the rotation axis decided to flip to a different orientation.
Why would there only be one angle? Why would there only be one axis of rotation? Like, why was originally everything just moving from one plane? Why don't they have multiple?
I can get this, Professor Parks, if you don't mind. So imagine a giant cloud of just random fucking pieces of matter that are all moving in random directions, but they have a little bit of an overall bias in one direction. Eventually, all of them will collide together. They'll hit each other. They'll transfer their momentum. They'll bounce off each other. And it'll cancel out most of the momentum except for the net momentum, the overall motion. And that will happen to be in one direction or another, but it'll only be one because you can only rotate on one axis over a large area. And so they'll cancel out and you'll get rotation that goes in one direction.
Well, wait
And
a
that,
minute.
kids, is why Venus and Neptune spin
Hang on, Larry.
backwards.
All right. Why is there's certain moons going in the opposite direction, though, right? And I'm sure there
On a
is
small
Their
scale,
accretion was independent.
absolutely.
Right. The objects in the solar system accrete independently.
Right. I thought they'd all be going in the same direction.
Overall, yes, but on a small scale, they don't have to. So it's sort of
And like
like
collisions can change your direction.
for sure.
Yeah, you could come up with anything in your model.
Not anything.
It's a
but
physics explanation. It's an explanation that we use from the physics knowledge that we already have.
I mean,
Yeah,
so you don't think collisions occur?
Yeah, how do I'm just kind of
Watch
curious.
Tora
about-
come in here and ask us to define what a collision is.
Huh?
Elastic or inelastic? That's going to be the follow-up question. Just immediately.
What do you say?
I said, watch
No.
Tora come in here and say, "Can you define collision for me?"
Speaking of collisions, at like what mass would rocks be able to hit each other and stick versus like break apart?
I don't think there's any real limit on what can stick versus what has to bounce off, unless someone can correct me.
I mean, everything's a little bit.
It isn't about mass; it's about energy. Because essentially,
Yeah, how it's dissipated.
yeah,
You want to lose your kinetic energy in the impact.
You also want the two objects to heat up enough that they fuse, but not so energetic that they split apart and blow up into small chunks.
So
Right.
if they hit each other and there's some source of energy to like be expended, so like you could have chemical energy, like maybe you have two explosive things hitting each other. If those hit each other, it's going to add energy from the kinetic energy to those explosive thingies that are hitting each other. They're going to explode, right? But if you just had two pieces of rock and they hit each other and they're really heavy to where their gravitational force is going to force them together more than just the elastic fucking repulsion, I think you're good, right?
I wonder how big the rock would. I don't know. That sounds crazy, but I wonder how big the rock would have to be for the gravity to overtake like
Sounds crazy.
the energy that would be exerted to break them apart, and like the reflect will basically be reflected on it.
You could model.
If you think about if you think about all the forces involved as it a mass gets big enough and it gets stronger as it gets bigger and it's collecting more stuff. As it's getting bigger, it's more difficult to move because its inertia is greater, and it becomes the primary attractor, in that region, and it's going to gather up everything it comes across.
Gather
They
it up.
already
But,
have a
like,
problem with forces. They already have a problem with forces. You heard Larry.
I'm just a little bit confused.
You can also just graph it out, right, as a function of v. You know the mass of your object, and then you can see what v's will be captured by your object because they have one half. Their kinetic energy will be 1/2 mv squared, right? So as long as you know the square of their velocity, you can figure out if they'll be captured or not.
So like at 100 miles per hour, two rocks that are like 100 pounds. Do you think that they'd stick together or break off? Is there like a program we can look this up?
They're on Earth for one.
No, in outer space.
I think this is an interesting question.
Obviously, what you're doing is on Earth because that's what you want to,
No, this would have to happen in space to form planets, right?
That happens in the asteroid belt.
Taylor, the other thing that you would have to look into is angle of attack. How are these two objects angled towards each other when they collide?
Yeah.
Okay. So we can figure this out just by figuring the escape velocity of two rocks, their combined mass of what? Sorry, I forgot the woman who was talking. Taylor, right? Yeah, you were asking about two rocks that hit each other at 100 miles an hour, right?
Yeah.
So I think all we need to know is their combined mass, and then we can figure out the escape velocity of their combined mass, and then see if that is more than 100 miles an hour. And if it is, then they stick together.
It
That'd be
also
awesome.
depends on
If you
it
could
also
do that, that'd be
depends on
super
the
cool.
composition
I'd
of the
love
materials.
If anybody could do that, that'd be
Materials matter
awesome.
because the materials are only going to make it more inelastic. They can't make it more elastic. So at maximum elasticity, the worst case scenario is they just repel each other at 100 miles an hour, right?
The material is going to affect the melting point of the object, which is going to affect whether or not they fuse together if you smack them together hot enough or hard enough.
Yeah, but haven't we landed on a few
Yeah, it's
asteroids where they're just
not
like
repel.
basically collections of gravel?
A collection of gravel counts as sticking together gravitationally, right?
I would think so. I don't
Not
know.
in the
Professor
same
Park-
way, no.
Sounded like someone said yes and someone said no.
I would contend that a gravel ball that is gravitationally bound is not the same as planetary formation. No.
That's fair. I think, yeah.
Okay, it's
I
probably
guess
not the same as a planet, but it's a. Well,
And that
I
would
guess this is
significantly
what-
affect density, right? Which would definitely, like, in that case, you're probably just going straight through the object, right? You're not really going to stop unless it's thick enough.
I don't
But
know.
even then, you're probably going to deflect a bunch of them, right? You'd be better off treating it as a point cloud than as a single unit in a collision.
Yeah, I'd love to see that. I've always wondered that, like, pretty much my whole life. Even when I did not question any of the mainstream narratives, that was the one thing I wondered is, like, if these rocks are forming planets, why wouldn't they just break apart when they hit each other? But somebody can help me understand. That'd be awesome. But I was going to ask. So basically, the sphere is the lowest energy form of an object. But then earlier I was told if it's rotating like a galaxy, then a flat disk would be the lowest energy form. Is that correct?
It depends on how much mass it has and how fast it's rotating, and yeah, that's pretty much right.
Yeah, like the sun is currently going around at about 220 kilometers per second, which is not particularly slow.
So like I'm just wondering,
Right.
like if the Earth is spinning, shouldn't it be more flat?
It's not spinning that fast. It's only spinning about 1,000
that's-
miles an hour at the equator.
It is also composed
that's-
of different material than a galaxy. A galaxy is basically gaseous, if you want to think about it. The density is far less of a galaxy than it is for the Earth.
It seems like that
Sounds
would
like
make
a
more sense.
protoplanet. Sorry, it's like a protoplanetary disk, right, guys? In your
Seems
view of the
like-
world?
A galaxy is not similar than a protoplanetary disk. They are both disks, yes. They both form from the same rough process, but they are not composed of the same things. They do not behave in the same ways.
I just want to know
Right,
because
and as I was mentioning earlier, the amount of forces involved determines what the resulting shape will be. So you can't just say all things are rotating should turn out as flat disks. That's not how that works. You have to use the forces involved to figure out what the resulting shape will end up being.
and where do I read about that? Like to see like which
Physics.
ones would end up being flat, which ones would end up being sphere, at these rotational speeds.
I just
You-
explained it.
You would
Yeah, where would I
need
go read
to-
about it?
So you would need to read an introductory astrophysics text would be a good start. I can try to look up more specific if you're interested in getting into the weeds of
That's
this
not where to
problem.
start. That's not where to start. You start with like an intro to Newtonian physics. You get down your.
Yeah, I've taken a
astrophysics
physics class.
Yeah, but
Yeah,
did you take it with
I've taken
calculus?
basic physics.
Wait, Taylor, was it calculus-based physics?
Well, then, I mean, honestly, you could just send me whatever, and I'll go learn about whatever terms I don't understand.
Yeah, you can learn about this shit.
Is there what equation is it for like if it's going to end up flat or round depending on the mass and such?
You would do the centrifugal force versus you would do the centrifugal force versus the amount of gravitation involved.
Both of them are pseudo forces, by the way, fictitious forces.
So, oh, good. So,
And that doesn't change what I said.
oh, okay,
Nothing
good.
exists.
So, yeah, I mean, maybe like if we can show that with the Earth versus like galaxy. I don't know. There's probably somebody who's already done it before on a paper or something.
Oh, that's fun because we can definitely show that the Earth is rotating because a mechanical
Wait, not just
gyrocompass cannot
rotating.
possibly work on a stationary Earth. It's not
Have they tried? Have they tried it on a stationary Earth just to see?
He believes
Or
it
am I
too.
going to get a
I would just want to reiterate the reason why they function requires the device to be rotating.
Haven't they tried gyro
So,
compasses in
Devices
space?
can't rotate on a flat plane, right?
That's not
that
what
what
I
it said?
said. The way that the
Okay.
device functions, the axis of rotation of the gyroscope has to point toward the axis of rotation of the device.
Okay, so you said it wouldn't be possible on a flat Earth. So why wouldn't that happen on a
That's
flat
not what I
Earth?
said.
Yeah,
Okay,
you
that's
said it
not what
wouldn't
I
be
said.
possible.
I said it would be impossible on a stationary Earth. I was very specific.
Didn't the
Okay,
person that
so
noticed
what's the
the
mechanism? What's the mechanism that keeps it from happening on a stationary Earth?
Because there is no axis of rotation of the device if it's not rotating, because obvious.
So it can't rotate because the Earth is stationary? Explain that.
It wouldn't
No,
align.
No, don't do that bullshit. Don't do that bullshit. What I
What?
said was the device the gyroscope within it, its axis of rotation needs to point toward the axis of rotation of the device. On a stationary Earth, with the device affixed to the Earth, there is no axis of rotation. Therefore, the device cannot function on a stationary Earth.
I don't remember you saying it has to be fixed to the Earth. Why would a device that's meant for finding the horizon or maintaining rigidity in space, why would it have to be fixed to the Earth?
It's got nothing to do with the
Don't say that.
horizons. Fucking
Don't they work in outer
completely
space too?
impossible to have this conversation.
Oh wait, hold on. Didn't the person that noticed the precession and the torque, basically resistance, like from the rotation, quote unquote, didn't they originally say it was because of the ether?
I don't care what they said because a gyroscope in its operation, it would in any reference frame would retain its orientation of its axis of rotation. That's what a gyroscope is built to do. That's its entire purpose.
Yeah. That's why they
So
built
then
it?
it can't
That's the
precess.
orientation?
Then it can't precess to true north on a stationary Earth. There's no way to make that.
Wouldn't it happen like if some well there's some other theories
other bullshit?
right, about how it could work. And like I said, didn't the first guy who actually recognized
some
it
other
say it
bull-
was because of the ether drift?
The ether drift has to conveniently press on this gyroscope, but only when it's rotating. The ether drift can't possibly press on this
That's a
gyroscope when
funny
it's not
thing to mention
rotating,
that.
which is really weird and something that doesn't make sense in any form of physics.
So isn't it also funny like how like the faster it rotates, like the more deflection it will have?
That is already explained in the physics that you're arguing against.
So let's just think about that. Like if it's just like measuring like a steady magnetic, if it's just measuring like a steady like Earth rotation, then why does it matter the speed at which you rotate it?
Not measuring Earth rotation.
Oh, it's not.
What it's doing is it's changing its orientation because the Earth is rotating. The amount of angular momentum available to apply torque is proportional to the angular momentum of the gyroscope. So that's what the explanation is in the physics that we're talking.
Ooh, if I could interject, I actually have the calculation for the earlier question. To get two rocks hitting each other and having an escape velocity of 100 miles an hour, you need a mass of about 1 trillion kilograms.
Super heavy.
The rocks are
You're going too slow.
What is this?
This is to have two rocks about the size of a softball that have an escape velocity of 100 miles an hour.
Get them to stick.
Wait. And so to get them to stick, they need a mass of what?
About 1 trillion kilograms.
Yeah, that's not accurate at all.
Can you send me that? That's crazy.
Correct me.
For escape velocity on the Earth?
No, an escape velocity in deep space where they're not affected by
If you're going to ask us to correct you, can we see your math, please? Thanks.
I use the formula. The escape velocity is the square root of 2 times the gravitational constant.
Can you post it in the chat? That way we can have it and not have to potentially misremember it as it's going across.
Absolutely.
Also, did you look at, does this equation involve the melting point of the material and the angle of attack of?
No, I assumed it's literally just the escape velocity of a mass of 2 times this.
That is the problem that I have with your approach, is because your approach is fundamentally flawed because you are ignoring a number of different things about what is happening in this scenario.
Well,
yeah, but
this
even
is
if they
the
did
worst
melt,
case
they would still
scenario.
bounce off. Even if
This
they
is the
did
worst
melt.
case. If the objects melt, that's going to eat up kinetic energy, and it's just going to make the escape velocity less.
I don't understand how you're using escape velocity in this explanation. What?
You should know.
I should know. That's why I don't understand how he's using it. That's why I'm confused. I'm asking for clarification.
If the escape velocity were less, okay, so if you have two objects colliding elastically,
Yeah.
and they repel each other, and then at the moment that they collide, right, you could treat them as one mass, right?
Well, at the moment they collide, you can treat them as one mass, but then why would you say they're also repelling each other?
Because they collide and they fucking collide elastically, so they bounce off.
Yeah, but then you're no longer treating them as one mass. I mean, we could do the derivation for the
Absolutely
equation.
could treat them as one mass.
We could do the.
So you're looking for the minimal mass necessary for two elastic masses to stick together?
Oh,
Not
so,
elastic, 2 solid masses.
Absolutely.
no,
That
elastic
would
is
be an
the way
elastic
it is.
collision if they stick together.
They stick
Yeah.
together because they're
That's
not.
an elastic.
Because of gravity.
It seems weird in the way that you're.
Gravity.
It seems weird in the way that you're stating this. You're stating that we've got an elastic collision where the elasticity is being overcome by the force of gravity between the two of them.
Yeah, they bounce off, then they bounce off each other, they slow down, and they come back.
That is not
Just
how
like
it
the
works.
rings of Saturn, they just continuously bounce off and they never land, even though gravity pulls things down.
Sir, Larry, the rings of Saturn have shepherd moons.
Oh my god.
Thank you.
There's going to be a bunch of moons.
That ignores the amount of rotational velocity of the entire.
Right. I'm assuming that they hit.
You say it has separate moons?
Suppose they hit at a glancing blow, that would just be even easier for them to stick together.
So they have separate moons. What does that prove? How did that follow? Somebody connect.
Shepherd moons. There you go. Go look it up. Do some research. Thank you.
Is it gonna form one big moon one day?
Wait, for this example about the inelastic and elastic collisions, what are we trying to find here?
How big do the objects need to be? Like, we're talking about planet formation. How big do the rocks need to be when they hit each other to just stick because of their gravity and not break apart?
I've put an excellent resource in the chat for those of you who are actually interested in learning about planetary formation.
I want to know like the mass of
Right,
them.
and I'm sure that we'll eventually get to the explanation for how a mechanical gyro compass can work on a stationary.
Well,
Oh yeah, I want to get back to that, by the way.
I'm pretty sure this is a simple problem, though. I mean, we don't care. Like, I'm just looking at the worst case scenario. So, what is?
You can find me later, Taylor, because this is not going to happen.
It is not a simple.
Actually, Taylor and Doofus, I have a question. I have a question for you two. I just wondered if you guys could help me out with this.
Yeah. What?
I'm going to give y'all a simple equation, and then after 5 seconds, I would like Taylor to answer, and then Doofus, I'd like you to answer, and if you see what y'all could tell me. What is the second derivative of 2x squared? Taylor?
I don't know.
Okay. Doofus?
Oh. You said the second derivative of 2x squared. Yeah. Jesus, I'm rusty. Hold on. 4x 4.
There you go.
It's 2.
4. Yep.
4.
You got it.
The answer is 4.
Just why would the objects bounce off of each other? That's what I'm wondering.
So to answer the question that someone asked Taylor earlier, her physics class was definitely not calculus based.
Oh, I don't remember learning about derivatives.
Yes.
Maybe I thought
It was
that.
not calculus based.
There are algebra-based physics class. I took one.
It was definitely not calculus based. I'll tell you that. It was for a biology degree.
Yeah, you shouldn't take
no.
physics class. It's not meant to be algebra.
Wait. Our marine biology department has to go through at least derivatives and integrals.
Yeah, I've never really learned about derivatives much.
Yeah, I have to take
You have to degree in biology and never study transitional fossils. So don't worry about it.
Transitional what? Yeah, we sure
fossils.
didn't.
Oh, okay,
We
got
learned
it. I'm trying to make it make sense.
and experiments, measurable scientific methods, stuff like that. Anyway, so I would like to talk about the planet formation, but I also do want to mention some things about the gyroscope. If you want to move on to that.
I do want to know about the planet because I took a physics class and this question's not clicking for me. Why would two orbital bodies that hit each other, why would they eventually bounce off of each other? I don't get that part. Like, why are we trying to find escape velocity? Well, there's a lot of reasons they could stick. I mean, the question, it would be basically a loss. It'd be the loss of energy, right? So like and then it's also the material and all of that, right? It's not just so simple as, well, they're two rubber balls hitting each other. You have to consider the loss of energy that occurs during the collision, and then you also do have to consider the gravitational forces for masses that large. But you're saying that it's
about smaller masses.
To Osna. So all you have to do is think about, like, what are all of the forces involved?
But you also have to think about the loss of energy.
Well, I mean, what is the energy loss going to be? It's going to be melting the planet, the two bodies that hit each other, right?
But the more energy that's lost, the less likely one is going to go off from the other.
That's true. That's absolutely true. But how
can
much
jump in.
energy is lost by melting or by busting apart rocks or what other forces you got versus how much energy was in the kinetic energy that went into the collision to begin with?
Well, we can do the derivation
argument,
together, but
hold on. The argument is that in the worst possible case, it's going to be an elastic collision, and they're just going to bounce off each other. So why not just make that the default case and then proceed from there? Like, I understand what went on. Like, there's nothing wrong with it. It's just it's fine because it's assuming the worst possible case. Just know that the actual number will probably be below that.
So I want to point out the rings of Saturn again, because the gas particles are being held down by the gravity, but the rings, whatever they're made of, gas, ice, whatever, dust, whatever you guys think they're made out of, it's not being held down. It's actually like in equilibrium because the gravity and the spin. But if the rings are spinning at the same speed as the planet, then why would there be rings to begin with? I don't understand that. Explain it to me like I'm a child.
Just 1 second. I am curious. They threw in another thing. They said, what would be the escape velocity of one of those things if it was an elastic collision, right? So now you're trying to figure out a velocity. You're trying to determine the end velocity, but you don't know the initial conditions either.
Why are we bouncing like this?
That's
what
Larry
says one thing, and then you say something else, and then Larry says
We're
something
talking
else.
about particles, right? Is that not a good example of particles bouncing into each other and not coalescing? I mean,
we did start.
I have no idea, Larry. So
I'm
going to listen to Osna's question, which sounded pretty good.
Yeah, I was here, and I was actually kind of curious about this question because now it kind of seems like we have two missing variables here. We've already determined the end velocity, but we're not giving an initial velocity either, and we're already saying it's going to be an elastic collision.
Can't let it go.
Okay,
So wait, they
just
did
to-
put initial velocity in.
Yeah, that's
What was
right. Taylor asked the question, suppose two rocks hit each other at 100 miles an hour. How big do they have to be to where they stick together because of gravity? And so the worst case scenario is that there's no energy loss from they hit each other, they bust apart, they hit each other, they melt. So the worst case scenario is that they just bounce off elastically. And the answer to that depends on their mass and their radius. So I just picked a fucking random radius of a softball, and the answer is it's about 1 trillion kilograms.
Yeah, I think. Wait, the radius. What's the radius you gave?
I picked
About a
10
softball?
centimeters, which is about a
Oh.
softball.
You guys can talk about the Saturn thing, and I'll try and see if I can figure this question out. Let's see.
Yeah, I'm trying to figure out this derivative thing. Apparently, I think that it was a faulty question to begin with.
So derivatives
What?
are pretty cool. If you can just imagine, like when you're driving in your car and accelerating, it just gives you the change from. If you had a relationship between at second one, you're at position. I'm sorry, this is too technical. I should think about my answer first. I'll just stop.
No, I want
the
you to
best
keep
way,
going, please.
the best way to think of a
it's-
derivative is it's the slope at a location.
Yeah, it's
Okay, so then how would
the
the
rate of change.
so
rate of
so let
change,
me.
yeah.
What was the question originally again? The second derivative of 2x plus 4. Is that what your question was?
Well,
2x
you
squared.
gotta know how to do derivatives. You're not gonna be able to figure it out without explanation. Unless you're
It's
like
super easy
reading.
to actually take a derivative of a function like that. You just multiply by the exponent and subtract 1 from the exponent. So 2x squared, you're going to multiply by the squared. You take the squared and multiply it, so you get 4x. And then you subtract 1 from the exponent, so you get 4x to the 1, 4x.
Oh, like
That's
so derivative would be like f of x,
Well, that's a
Exactly.
function.
the
Yeah.
function of x. Okay, maybe that's not because we never use the word derivatives. Like we would use just like f of x to solve the problem.
F of x
No,
just means
that's
function.
algebra. I mean, f of x is just a function, algebraic function. The derivative is in calculus.
You did derivatives,
How would you
but they
wait
never
that?
called it a derivative?
So
Yes, you know what f prime of x is.
It's
Does
not a
that
big
ring a
deal.
bell?
that's
Wait,
derivative, yeah.
How would it be written in calculus then?
It would be written as
You'd
f
have-
prime of x.
Yeah, you'd have a little apostrophe.
Or
So,
can you
F
tell me
apostrophe
dx dt is also a derivative?
Leibniz notation is better.
It
I
is.
will agree.
Actually, no, I like. I can't remember which is the
Taylor,
two. I
I'm
like the
putting
dot
the
notation better.
in the chat. Taylor, I'm putting the notation in the chat.
I like Leibniz because it really encourages you to treat it like a fraction, like mathematicians hate, and then I get to feel like a proper physicist.
Okay, I hadn't thought about that, but yeah, irritating mathematicians is definitely a plus.
But then I'll also, so my physics professor, I irritated his soul because he had an integral for us to answer a question, and its solution was like pi times some integer. So I just put pi times some integer, and he's like, I don't like this, and I was like, fine.
Do you think that it's like reasonable to like if somebody's having a conversation to like go ask them a random question if they can't answer a random question, like to then like not listen to what they're saying?
Which question do you
The
think was
only way the
random, Taylor?
Glovers could win.
I'm just curious. Like I would never go up and ask somebody like a random math question, and then be like, yeah, what's the
While your
answer?
answer is it depends.
That's how they win, bro. If you can't answer the question, they automatically take that as a feather in the hat.
Well,
Wouldn't
if
that be
we're
like
talking about
genetic
physics
fallacy or-
and math, it becomes important to know how you're approaching physics because physics at its core is just an application of math.
So somebody.
Oh shit! I thought physics was science, bro. How many
Yes,
like math
no.
credits do you get when you take physics class? You get a bunch.
A shitload, yes. Taylor, I got a different answer to your question. I think that you should ask rhetorical questions when you think that it's going to get them to think about the answer and like really learn something, or maybe realize there's a gap in their understanding and that they should listen to your answer. But frequently, yes, it is just used to prove that you're smarter than the other person, which is an asshole move. I kind of agree with that take too.
Yeah, I mean, honestly, like I wasn't making any like positive claims about anything, so I'm not sure like what like what claims you'd say that people shouldn't listen to me because I don't know physics or whatever. Because I wasn't over here like making some positive physics claim based on mathematical equations or anything.
No, it wasn't about that, Taylor. It was about how best to explain it going forward. That's all it was about.
Okay.
Taylor, I think everybody here likes you and thinks you're a nice person that's trying to understand something that you don't understand, which is admirable.
Okay.
But
Well,
there is
honestly,
a difference. There's a difference in how I would describe like a force to somebody who's taken calculus for somebody who hasn't.
yeah, you can just ask if you were going to explain mathematically about this, planet formation or whatever. You can ask if I understand a term or whatever. You don't have to like come and give me like some random.
I wasn't
stuff.
I wasn't the one who did that. I'm just trying to provide you a rationale that isn't necessarily people trying to be mean to you.
No, it's okay. I'm just saying that doesn't seem like a good way to have a conversation moving forward because anybody can ask anybody some random question. I don't know. It just seems like ridiculous. And usually I don't even entertain that stuff. Like if I have had people try to do that to me, just ask me a random question. Usually I'll just say that I'm not going to participate or whatever. Even if I have known the answer, I've just said I'm not participating because I don't
the point
agree.
I'm making, Taylor. It's not a random question. It's directly pertaining to how the explanation will be going forward.
So were we going to use that mathematical formula to explain planet formation or something?
Well, it would be helpful,
Like,
right?
you're so good.
Yeah. So I don't even think that equation was relevant.
Most astronomy involves calculus.
That's great. So nobody even posited like some equation to explain this. The only one I've heard is somebody who actually came up and tried to give like the math.
Right, because you've been talking and complaining about being asked about this.
Wait, I also did try to explain it. Didn't we just go through the elastic
We did.
equation?
Yeah, we did. But I'm just saying that equation didn't even pertain to that.
It does though.
Can you explain? Can you give me the two equations, the elasticity equation, the rate of velocity, escape velocity equation next to that?
Well, I can give you some of that.
Escape velocity.
It's not an elasticity equation, but I did figure it out.
Elasticity
And it makes,
equation.
I don't know what that is, but what it has to do is that the kinetic energy after the collision occurs has to be equal to or less than gravitational potential energy, which makes sense. So it means that the amount of how do you explain this the other way? I don't know. Yeah, it's basically the amount of energy that the objects have as they're moving apart. If it's greater than the force of gravity trying to pull them together, they'll escape each other, and if it's less than, they'll be pulled together. Right?
Yeah,
So,
I understand that completely.
Yeah. So
I have to say, Taylor, you have a lot of integrity. Appreciate you being here.
So that would be So you need the equation for kinetic energy, 1/2 mv squared. I don't actually know what it is.
That's kinetic energy. It's 1/2 mv squared.
Yeah. You need that
how
one,
does this
and then
explain star formation?
well, because we're discussing two masses
No, I
hitting
want to
each
know about
other.
planet formation. Like, what size bodies would you need for them to stick versus not?
Oh, the question is what was the initial velocities they were moving at, and then what are the sizes of the masses, right? Because the mass is in 1/2 mv squared. That m is the mass of whatever it is. And then you basically just have to do set the equation. It's kind of weird. It's like 1/2 mv squared plus 1/2 mv squared, each of their kinetic energies. And then you basically have to have, since you're saying they're separating apart, it becomes a little weird because
no one says they're separating when they apart. That's another problem that you have with this analysis.
Well, I'm not saying that I said that. They're asking about that.
So the other thing is there's not really a way to phrase what's the mass needed, because any point in space that has more mass than some other point in space is going to attract that mass towards it.
Yeah,
but how would they meld? Like, I don't know. We can discuss it later.
Well, they meld because as they come in, they get more and more kinetic energy, and eventually they're coming in so fast that the kinetic energy that they're imparting can't dissipate away fast enough through radiative processes. So it increases the temperature of the material, and then it melts. And then when it melts, it separates by density, which is why the Earth has like the molten core with a lighter crust and mantle.
Yeah, I can get that with a big body, right? Thinking about it, but I'm talking about planet formation in the earliest stages where you just have.
Well, at the beginning, right? They're going to be little things popping together and going, and they're just going to like that. That's how it goes. It goes from small to big.
Yeah.
Like so, the mass is kind of arbitrary. There's no needed mass. It's just as long as I am the plot spot with the most mass, everything comes to me.
Melodic, you have a lot of expertise in this, it seems. Do you have any sort of source that you can share that explains or demonstrates this for the audience?
I mean, like rocks of like 1 foot diameter or something.
It's not the diameter. What matters is the mass, right? Because the mass is determined how much kinetic energy it has before and after the collision, and it's also determined how much gravitational potential energy they'll produce. What really matters is the mass. It's not the size of the thing.
I said like 100 pounds earlier.
Right, so like 100 pounds. I don't know what that is to kilograms.
This is a far more complicated topic than people are presenting.
Oh yeah, I was very hand wavy. Please, Professor Parks would be the best person. Professor Parks would be the best person to answer this question.
Yeah, 100 kilograms will be fine too.
So my answer, as I said before, there are a number of variables that need to be taken into account, such as, like I said, angle of attack, what the velocity of the object is, what its density is, things of that nature. And to blow your all minds, just because I know Flat Earth is going to love this, the first force that actually starts the accretion process is actually the electrostatic force.
Yay!
What about poor old gravity?
I knew that was coming from Professor Parks.
Throw gravity under the bus.
So I mean, initially, if you think about it, I mean, actually, try to picture what's going on. The big, like a
electric,
full of dust and from grains of sand up to larger, we'll call them all asteroids, and they're all on different paths. All of it's on different paths. Some of them have huge ellipticals, and some, initially that electrostatics, things are just kind of sticking together, joining up, and then they get, one gets so big that actually gravity starts taking over the collection of the stuff in its path. It's pretty amazing if you think about it. It's pretty wild to think about.
So, Professor Parks, I wanted to bring up, the electrostatic force and cloud formation, right? It pulls it in, right? It pulls it all together, but there's limits to it, right? It can't compress it to the point to where it just keeps compressing, and like with a with a star formation, and I know that's not planetary formation. I know it's a little bit different, but it's the same concept. There seems to be like no limit how hard that they can press the gas together and create stars. Why is there such a discrepancy here?
There's a force that stops the electromagnetic attraction. It's called the Pauli exclusion principle, and it's a fundamental thing, and it just fucking overcomes it.
Okay, I don't know what you're talking about. Larry, what do you mean by electrostatic? First off, a protostellar cloud collapses via gravity, not by electrostatics.
Okay, so these clouds, gravitational collapse is creating these vacuums that are, have lumpy gas in them, right? So this lump of gas, I guess what you would call like a gas giant, right? How come it doesn't like expand back out? Because you can't demonstrate on Earth where the gas pressure is being held down by gravity despite the container being open. It'll reach equilibrium or
the atmosphere.
Yeah, but they don't think that's. They think the firmament.
Bucket of heavier than air.
I'm not really trying to argue about that. I'm trying to argue about like star formation. Like it seems implausible that the weakest force would be able to grab all these particles and turn them into a nuclear fusion.
I don't think you understand just how many particles it is, Larry.
Real quick, Larry, what would stop them from coming together?
The gas pressure. The elastic
Why would
collisions.
Where does pressure come from?
Okay, can you explain that? Yeah.
Well, according to you guys, gravity. No. According to you guys, gravity. That's what he just said.
Gravity's pushing it inwards. It's pushing it outwards.
Elastic collisions.
I would like to hear Professor Parks describe it.
I would too. I'll shut up. I'm going on mute.
I'm still getting confused as to what's going on, but I can just give you a very quick rundown on how a planet forms. You start off with a giant molecular cloud. That giant molecular cloud has denser pockets within it. Those denser pockets will cause a larger effect of gravity, so gas begins to collapse in around those dense pockets. That's what we refer to as fragmentation. If you look at those fragments, or now planet or stellar cores, that core is going to have an overall rotation. As the cloud continues to collapse, the center is going to collapse faster because gravity is distance dependent. So that will start forming a protostar. The rest of the gas cloud will spin up and form a disk. Now, going back to the protostar will get to a point where a sufficient enough amount of gravitational potential energy has converted into thermal energy. At this point, gravity has a competitor. You have thermal pressure, which is pushing outward, and gravity is trying to push it inward. At this point, the star begins to contract rather than to collapse.
Did you just say inward?
Towards the center of the core or cloud.
Oh, I'm sorry. I thought you said the inward.
No, centered. No, I hope I didn't sound like that. Anyway, so okay, I don't know. I did not mean to sound anything like that word.
I'm just kidding. I was just busting your balls.
He's just throwing you off your groove, Professor. Continue. You're doing great.
So the star begins to contract. The problem, what occurs is that the thermal pressure is never going to be high enough to arrest the gravitational collapse. Basically, the gravity is going to always be stronger than the thermal pressure. Again, because gravity is distance dependent, the core of the star is going to be collapsing faster and getting denser and more and hotter before the surface does. At some point, the pressure and temperatures get so high, the temperature is around 10 to the 15 Kelvin. At this point, the electrostatic force that is preventing the protons from basically slamming and forming helium gets basically overcome. You have this process called quantum tunneling. Not going to get into that, but effectively you get conditions that are correct or appropriate for nuclear fusion to occur. So hydrogen atom protons start fusing together into helium. That process produces energy. That nuclear radiation pressure will then kick in. That will stop the incoming fall of gravity, and then you will have a star that is in what we call hydrostatic equilibrium.
I got a question for you, Professor. You familiar with the YouTube channel LPP Fusion? He's a doctor. I forget his name, but he talks about the helium problem. I think is it the helium catastrophe, helium problem? I can't remember. One of those two. He wrote a book about it in like the early '90s. Are you familiar with that channel?
I'm not familiar with the channel. I've heard the term helium catastrophe, but I've honestly haven't looked into it.
Right. Well, he talks about it. LPP Fusion. I can't remember the guy's name. He's one of my favorites. Please look into it. I think he worked for NASA.
Oh, you cut out there, Larry.
Oh, I said he works. I think he works for NASA, so he's like a legit scientist. He just doesn't always go with the grain, if you know what I mean. He kicks the sacred cow from time to time.
Okay. LP. Yeah. What is that called?
LPP.
LPP.
Once Paul Fusion.
I'll check.
Maybe he's ahead of the curve.
But is he behind the curve? That's the real question.
That's also possible, right? I can't remember his name. I'm gonna look it up because I can't remember his name.
Or is
I'm
he
gonna stop
fun of the
right
cue
That was
ball?
supposed to be a flat Earth joke. Anyway. So, Larry, does that answer your question?
Yeah, it's a pretty good explanation. Of course, I think it's
Wrong.
open to interpretation. No. I think it's open to interpretation. I'm not going to say whether it's right or wrong because I don't make claims about heavenly bodies, except for they look like lights to me.
No, but you do disagree with Newton.
I don't think I ever said that. Are you putting words in my mouth to win a debate?
I
Is that
mean,
how you win?
you were the one who said that you had to add
But-
stuff to.
But the question is, Larry, do you want to know more? Do you want to understand the things and how the universe works?
Well, I got a great deal of respect for this professor here. He's always treated me kindly, and I believe that he's acting ethical when he's in here. So I don't mind listening to him and saying that I don't necessarily agree with him, but we can agree to disagree. That's fine. He's just talking about star formation and planetary formation, which I wouldn't even begin to claim something like that. So that's on him.
You disagree then?
Professor Parks is getting better.
No, I don't have an opinion over it. I don't know if it's true. I don't know if it's false. I'm not saying I disagree.
So therefore,
It's
you
very
have an opinion
powerful.
We should all be respectful.
It's very powerful to just sit on the fence and look at all the information. It's a powerful place.
Yes.
Cowardice
did try
is
to
too
question-
powerful, and self-denying cowardice is even
Yeah,
worse.
so Taylor, I tried your question. You just run into a lot of issues because you do have changing forces, especially because the strength of gravity is going to change after they hit each other if it's going to be an elastic collision. So it's just a lot of calculus that I don't know how to do. I'm sure you can find it somewhere. It's like not a simple question, even assuming perfect conditions, even assuming no mass change between the two objects. It's very difficult.
Earlier, Tony was saying how much I suck over and over. I don't know why he started doing that.
Well, that's how you know that their arguments are working really well when they resort to things like that. She probably does suck. I'd imagine she's a terrible sailor. Like, I wouldn't want her on my boat if I was a sailor. But I bet there's other things that she excels at. Probably not sailing. You suck at sailing, is it true?
Maybe she's good at selling or like sales. So I apologize for talking.
All right,
Can we
Ty, I
not talk
can.
about how Taylor sucks? Can we just move on from that?
Yep, Taylor is
That
a
would be
sucky
preferable.
sailor.
If we're honest here.
Keep it moving. Keep it moving.
Okay, I did want to mention something interesting with the gyroscopes that I was learning because remember earlier we were talking about rotation. So I brought this up a while back, but I've been looking a little bit more into the Burnett effect. Whenever you have a rotating body of either magnetic or non-magnetic material, it'll actually produce a magnetic field. And so I thought that was really interesting. And the faster you spin things, the higher the magnetic field will be. Same thing with the gyroscope. The faster you spin it, the more precession you will get in the torque. Just a fun fact. So yeah, and there's other effects too. What is it called? There's another one for electromagnetism that's generated like basically with spinning bodies. But when they first looked at the gyrocompass's precession, they did attribute it to the ether. I'm just saying, and then I just how later that was transitioned to Earth rotation. Does anyone know how that transition
Wait,
happened?
hold on. I took a physics class and I literally just now understood how gyroscopes work. That's so crazy. They're able to move freely in the fact that the thing they're moving on moves. The gyroscope itself wants to stay in the motion that it's in, but the thing around it moves because that's what it's attached to. It's attached to the Earth. So it just looks like the gyroscope is moving even though it stays in the same place in space. It's just a thing that is caging it moves. I literally just got that right now. That's crazy.
Yeah, it's pretty dope.
Yeah, that's cool.
Wait, Taylor, you said that originally they attributed it to the ether?
Yeah.
What?
Yeah, I know. Gyrocompass. Yeah, gyrocompass.
Gyro
Yeah, we
compass.
can't just pass that.
How did you ever come to that conclusion? It's very designed it because he knew that the Earth was rotating, and that was the basis behind it. How do you think that was attributed to aether drift?
Well, I've never actually read that the gyrocompass was originally made to say that it was looking for Earth rotation, but yeah, so it was experiments like the Sagnac effect designed to detect the presence of the luminiferous ether. Let's see.
Sagnac effect was not using a gyro compass.
Foundation for optical Sagnac experiment
using a light-based interferometer.
for the optical gyrocompasses was explicitly described by its inventor as evidence for the ether and early precession navigation devices like gyrocompasses.
Maybe I'm super behind. What the hell is ether?
It's the medium which everything exists. So like how like in a vacuum, like these particles can like pop in and out of existence, like in the vacuum space time.
That's what a vacuum is.
It's
It's
an
a lack of
old-
particles.
It's an old debunked idea in
Talking about
physics.
quantum foam.
Yeah,
Well,
quantum.
I mean,
Yeah,
it might not be super well defined. Is the ether different than just space?
the quantum field. It's like
So
an
in the 19th century, In the 19th century,
And it was a
scientists
rarefied gas that was needed in order for light to propagate through.
yeah. In the 19th century, scientists realized that light has wave properties, and it's not particles like Newton thought. So therefore, they changed the way they went, and since everything they'd observed needs a medium in order for a wave to be, they were like, oh, there must be some medium that light travels through to us. Then you get to Michelson-Morley, which gets referenced by flat earthers all the time. They were like, hey, if there's this thing, we should see it. They didn't see it. Einstein came out with relativity. We discarded ether.
Okay. So it's
So
basically
basically,
like the
it's the
water
fifth
of
state of
existence.
matter. It's the fifth state of matter. So earth, air, fire, water, ether. So earth is a solid, fire is the plasma,
Air, fire,
water's a
water,
liquid.
states of matter.
I use it to start my tractor.
Yes, solid, liquid, gas, plasma, ether. And ether is the vacuum energy that destroys your model.
Okay, wait, just depending on how you do fluid dynamics, like air is also a liquid.
Fluid. Water's liquid. It's a fluid.
Yeah, but air is also considered a liquid when you do like fluid dynamics.
What's a fluid?
No, fluid,
It's a
not
gas.
liquid.
Not a liquid.
Yeah, I know it's not like it's literally not like the state of matter, but like when you do certain physics problems, you like do it like air isn't considered. It's like
A fluid, not a liquid.
yeah, I
It's
know.
fluid.
It really is a fluid, not a liquid.
It's okay. Flat earthers can be right sometimes. Okay.
You name things that weren't states of matter, but okay.
Right, fluid
Well, I mean,
dynamics is about fluids. It doesn't really care about liquid versus gas. So you kind of might treat them the same, but you call it a fluid, you call it not a liquid.
Yeah, I mean,
Fluid
a
means
a
non-solid.
pneumatic system's different than a hydraulic system, right? But
So
they're all
plasma would
the
be a
same
fluid.
equation. Thank you, Larry, for interrupting me. It's appreciated.
You're welcome, bro. It's an open mic. I didn't do it on purpose.
Like when I take advantage of the open mic, you guys really hate that.
Well, at least I don't scream your name, right? That would be weird, right? Only my
You
wife should
scream
be
my name
screaming
all
my
the
name.
time. You do that all the time, bro.
I don't even know your fucking name, bro. What are you talking about?
You absolutely know my name.
I have no idea who the fuck you are, bro. You're
Okay.
hysterical.
Okay. Anyway, so ether is a big no-no.
Well, it's not necessarily a no-no. It's just like mostly debunked. There's some guys who are kind of trying to use the name to describe some theoretical stuff, but they explicitly note in their first paper that introduced it that this is not the lumen